There's a checksum in the TCP and UDP header. The IP checksum is only there in IPv4. IPv6 does not have that. That is not an advantage, but I'm getting to that later. The checksum algorithm is actually very, very, very simple. All that's done is you build the sum of the one complement of all words in the packet, or the section you want to checksum, and take the lowest word of that. Super easy. The IP checksum only covers the IP header. We will see why this is important. It does not cover the payload, while the TCP/UDP checksum does cover almost the entire packet. Specifically, it includes the payload. It does not include all of the IP header. It includes a pseudo IP header. We'll see where that comes from and why it's a bad idea later. It includes the entire protocol header and all of the payload. Anybody have a beer for me? No. Performance consideration, we're talking about checksumming. I mostly care about the forwarding case. When we talk about the case where the connection is locally terminated or sent through relay B or something else, the total cost of the packet processing in the kernel doesn't matter anymore, because the other stuff is much more expensive in comparison. Like packet processing in the kernel is, compared to stuff in userland, pretty cheap. The math to do the checksum is dirt cheap, can be considered free. I spent almost 10 years now in profiling the kernel and finding where it's spending the time and where the bottlenecks come from and so on. So I have a pretty good idea of what's going on. The calculation, as I said, can be considered free. You cannot even find that in the profiling output. The cost is a different one. The cost is latency and bandwidth to the memory. In modern CPUs, you're mostly talking AP64/i36 here. It's also true for other modern designs. You are completely incapable of getting the actual integer units to be busy. It's basically impossible. Like, that's never ever a limit. The limit always is some kind of latency. Sometimes bandwidth, usually latency. Can be the latency between the decoders that take your sys instructions and decode them into the little micro-ops they work with. Most of the time, it's the latency to the caches. When the stuff is not in cache and you have to talk to a memory, then the CPU is idling for several thousand cycles. Memory is really, really slow compared to the speed of the CPUs themselves now. And also, another case to consider is the latency to the device you're talking to. So if you're talking to the network, we're talking about latency on the PCI or PCIe buses or whatever in the card zone, right? So that's our limitation. Checksumming hot data, stuff that is in cache, is basically free. You do not even find these things in the profiling graphs. Or it's somewhere way down below. But it doesn't matter, it's free. Since the IP checksum only covers the header, and you, by definition, have the header in cache when you forward the packet, because you need the header information, right? That is free. Which is why not having the checksum there is not, for v6, doesn't make a difference. That's not an advantage. We have to checksum data that we have to fetch from memory. That is expensive, because, as said, the CPU will idle for a long time waiting for the data to show up. The TCP and UDP checksums covering the entire payload have exactly that problem. The IP header will be in cache, no problem. The TCP header or the UDP header, likely. The payload is almost guaranteed not to be in cache. As said, the locally terminated connections are a completely different matter, but those don't matter because then the cost of the local processing, the upper layers in the stack and foremost people, is so high that this is negligible. Some platforms have optimized checksum code. This is actually kind of interesting. i36, Spark64, and SH have assembler implementations for the checksum algorithm. And a couple of other platforms have optimized C versions that might contain assembler code as well. I didn't check them all. Oops. It's a very good question whether the optimized ones are actually faster. We had many, many cases where assembler implementations were slower than C implementations because they were 20 years old or 10 years old and made assumptions about CPU architecture, internal workings. Well, they made assumptions that are just not true anymore, and the compilers became much better. So it would be a very, very, very good thing to actually measure whether these optimized versions are still faster than the generic C version they have. That's a project for somebody of you. I don't want to do it. It's easy. So please do it. So speaking about the IP checksum, that's the entire IP header. As you can see, it's pretty small, right? There's two things in here that we care about for the checksum now. The checksum itself sits here, and the checksum has to be updated by each and every router because the time to live is updated by each and every router, and the checksum has to be recalculated, right? As said, since it only covers the header, you have the header cache anyway, not a performance problem at all. Pretty much each and every modern network interface card is an offload engine for checksumming. For the IP checksum, that basically does not make a difference. Because, well, as I keep mentioning, calculating it is basically free. The checksum implementation of OpenBSD, the flow through the kernel I explained many times, so we're taking the shortcut here. Basically, for the layers I care about, we're talking about IP input, calling IP forward, going to IP output. In IP input, we have the decision whether a packet is to be locally delivered or to be forwarded or to be thrown away because it's routable. And right after that, there's the PF test call. That's the entry point into PF. So PF is there. If it's local, it's handed off to the upper layers, and as I said, I don't really care about that. If it's to forward, it goes to IP forward. In IP forward, we do the routing, kind of. The routing lookup actually happens in IP input, but that's a different story. Do the TTL decrementation, and in case it's unroutable, generate the ICMP error to be sent back to the source. In IP output is a long beast. Most of that code deals with locally generated packets that do not have the header fields filled in at that point. So IP output does that. Surprisingly, it also calls PF test for the outbound PF check. And right after that call to PF test, the IP checksum is recalculated unconditionally, always. You have to recalculate it because of the TTL decrementation, right? Locally generated packets at that point don't even have a checksum. Point is, after PF, the checksum is recalculated. PF had a lot of code to deal with the IP checksum. Whenever we did code, whenever we rewrote something in the packet like net or redirects or the scrubbing stuff, we updated the checksum to compensate for these changes, right? Well, that was completely pointless because the checksum is replaced afterwards. So that code could I could almost just remove that code. Why not? Well, there's a case to consider, the bridge. When you're bridging, you're obviously not really looking at the IP header. Well, we actually kind of do if you want to filter, but bridge is supposedly layer 2. It isn't really, but it's supposed to be this layer 2. The bridge did not recalculate the IP checksum, obviously, because it's in most cases, well, in theory, let's put it that way. In theory, the bridge does not modify the packet. And that is actually true unless you explicitly ask PF to modify the packet. If you don't do this, the bridge doesn't touch the packet, just sends it out to the one or multiple other interfaces and be done with it. Point is, no handling of the IP checksum whatsoever. Just having all this code in PF just for the bridge is kind of ridiculous. So the solution to that problem is to make the bridge behave. So when the bridge calls PF, and PF tells the bridge that the packet has been modified, just recalculate the IP checksum. That was actually pretty easy and straightforward to do. And I could basically delete all the checksumming code in PF. But now there's the checksum offloading, and it's getting into the way. I'll explain why. The bridge can use the offloading actually. Even in the case of the bridge replacing the IP checksum, we can use the offloading capabilities of such a network interface tab. But, wrong slide. The checksum offloading. I'll quickly explain how that works. As said, pretty much everything made in this century and the 10 years before has offloading capabilities, at least for IPv4. The other stuff is irrelevant anyway. Our stack has had IP offloading capabilities for ages. Like, I didn't really check, but this must be 2000-ish, but for a long time. How does that work? We had code that at the point where we had the checksumming calls, but they always have been in the network stack, they have not been moved. There was code to check whether the outbound interface has checksumming capabilities. If so, there was no checksumming being done, just flags set, indicating that the packet needs checksumming and the hardware will do it. If there were no checksumming capabilities, we couldn't solve that. On the inbound side, the driver gets the offloading, the checksum verification result from the hardware, from the offloading engine, and sets flags in the env header, in the packet header, indicating whether the checksum was good or bad. So if we see such a packet, it either has a flag saying the checksum was good, the checksum was bad, or it has none of these flags. If it doesn't have any of these flags, it's obvious that we need to verify ourselves in software, right? The bridge. The bridge is special case all over the network stack. It's annoying as hell. The root cause is the irregular behavior regarding checksums. All other output paths take care of the checksum. The bridge doesn't. Because, yes, in theory, it shouldn't modify the packets, but that theory isn't true anymore. Like, it hasn't been true for 15 years. Once the bridge is fixed, all the special casing all over the stack can go. So I want to do that, right? While what I did, and I removed all that code, and I think I even committed that. And a couple of days later, no, I didn't. No, I didn't because testing showed the case was covered in testing, fortunately. There's a gross hack in the bridge that I discovered in that. The gross hack is regarding broadcasts. So a broadcast packet. The bridge basically deals with the broadcast packet like it does with every other packet, and at some point when it has already decided where to send it, it's using the first interface on the list or something, it kind of randomly picks an interface for a broadcast packet, looks at those capability flags, whether the interface is checksumming capable or not, and then just before sending it out to that interface, wait a second, this is broadcast, this needs to go to all interfaces. So it copies that packet and puts it into the outbound queues on the other interfaces. Now this is after the checksumming decision stuff has happened. They're taking a short circuit. Well, whenever you're being super clever and taking a short circuit, most of the time you're being stupid. And this is what happened here. Somebody thought he's clever, but actually this is not clever. This bites back later. It always does. I did not fully track this down, so I did not fix this yet, because the entire journey is, the entire thing is super complicated, and I didn't want to get too sidetracked. So I put the special casing back in and moved on. At some point, this needs to be fixed. Status. With that, I could remove all IP checksum handling from PF. As I said, the bridge special casing is still there. Basically, if an interface, if a packet touches a bridge, we always do checksumming in software. That's all we can do for now. That's been the case forever, basically. That's been the case forever. It's kind of sad, since it is possible to use the offloading engines if there wasn't that broadcast bug. So at someday it'll be fixed. As said, this does not make a difference for performance, because the IP checksum is free to calculate. I did performance measurements, but you can't measure anything. Like, benchmark as much as you want. The differences with and without IP checksum offloading are within the noise, so it doesn't make a difference. But with the changes I did, the code is considerably simplified, much simpler to follow, and the IP checksum handling is now in one place, nicely self-contained and not spread all over the stack, the little joy disease. The IP checksum handling in PF was just plain wrong. That's another sign of a, I'm not sure I want to call it a problem, but in the early PF days, all of us who worked on PF were PF hackers, not network stack hackers. We were PF hackers. So we tried to do everything in PF and didn't look at the rest of the network stack all that much. That has changed. That has changed a lot. But that's the reason for this. Like, we're doing something to the packet. Oh, the IP checksum doesn't match anymore. We have to do something about it. Nobody really had the read checksumming code in the stack on the radar back then. So a lot of code written for nothing. This should have been fixed in the bridge 10 years ago, but it wasn't. Now it is problem solved. Coming to the protocol checksums. This is mostly TCP and UDP. ICMP has a checksum. Other protocols are uncommon. If they have some checksum, there's no offloading engine, there's no generic support, then that's a protocol or even application level thing. That's nothing we care about. The protocol checksums only cover parts of the IP header. Why? If they would cover the TTL, for example, you would have to redo the checksum on each and every router. And as mentioned, it covers the entire payload. So that is not free performance-wise. Also, the router shouldn't need to know about TCP or UDP. It only needs to know about IP, right? So that would be a layering violation. The question why the protocol checksums cover parts of the header of the IP header is a very good one. I can't answer that. It doesn't really make sense. The recalculation here is potentially expensive, not because of the math, but because of fetching all that data from slow memory or wherever it might sit. The handling in PF is just the same that we had for the IP checksum, updated on the fly whenever we make changes to the packet. And that's the beauty. Nested calls to a fix-up function. This is ugly as hell, and once again, the IPv shitcode is even more ugly than the init code. In these nested calls, these weren't even the longest ones. There are longer chains. In these long chains of nested checksum fix-up calls, it's really easy to screw up. It's really easy. Even a nasty compiler doesn't notice because we're dealing with words. Each and every parameter is a word, right? Almost. Whenever we touch a packet, we have to do the checksum fix-up. And we have to do this per word. The checksum fix-up function needs the old word, the new word, so that it knows what changed, and it basically applies the delta to the checksum. This is kind of clever, but per word is not clever. I have to get into the inner workings of the stack a little bit more. This is kind of interesting because in this we'll see an old hack from the BSD network stack that nowadays made it into hardware. All the BSD derived network stacks use so-called protocol control blocks to deal with TCP and UDP connections. That's to track connections and to keep state. UDP being connectionless does not mean that it does not have state. The UDP sockets need some kind of state, right? And that's being tracked in protocol control blocks. In short, they're called PCBs. And they're being looked up using hash tables. In OpenBSD, the PCBs can get linked to PF states. If that's the case, we save a lot of hookups, of course. When a socket is opened by a usernet application, a PCB is created. That's called a template PCB. The easiest case is a socket, like the server-side socket. You bind and you listen on it. So you already know the local IP address, and then you listen for incoming connections. It's pretty much the same in the other cases, but that's easier to follow. The known parts of the connection at this point are already filled in the template PCB. And these are already checksums. Now, of course, this is a hack. Where's my strong language about that? Oh, later. When we accept a connection on that socket later on, the template PCB is copied. The other side's information, like the remote IP addresses and ports and whatever else, is filled in, and the checksum is just updated. This checksum still is not good for anything really, because now it only covers a little bit of the headers, right? But it's supposed to cover the entire payload. The entire thing, a couple of fields from the IP header and the TCP header, it's called the pseudo. No, just the IP header, sorry. It's called the pseudo header checksum. The packet is then marked with a little flag for I need checksumming and is passed on. Very late in the outbound code path is, actually it's late now, it used to be earlier. We look at those checksum flags and we basically compare to the interface capabilities. If the packet has a flag, I need a IPv4 checksum and a TCP-v4 checksum, and the interface can do it, you're done. Just pass it on, set the flag so the hardware knows that it has to do it, done. If it needs checksumming and we don't have any offloading capabilities, we obviously have to do it in software. As said, the old way, this happened pretty early. I changed this so that we basically work. I'll come back to that later. If it does not need any checksumming, because the packet is forwarded and has not been notified, it's obvious that we don't have to do anything, right? So we can go over here stuff. The pseudo header checksum, that's a hack that might have helped on the HP300 on the VAX. The VAX is actually fast, HP300 is slow. On any hardware modern system, this is counterproductive. This incremental updating doesn't make sense. Modern systems work with pretty big cache lines. Those systems have tiny caches, if at all, right? Modern systems have big caches and big cache lines, so that stuff is cached, and there is no cost doing this at once. Doing this at once is cheaper. The incremental updating complicates things very, very, very considerably. Foremost in the code, so foremost it's a pain for us working with the code. This hack, some network interface card vendors eternalized this hack in hardware so it'll stay. There are some chips, foremost the internal Broadcom ones, that require the pseudo-header checksum to be there, and their offloading engine only takes care of the rest, updates the pseudo-header checksum. Everybody else who implemented checksum offloading capabilities did the right thing and just ignores what's there. They don't require anything. They do the full checksumming and write the checksum to the packet, done. There's some that require the checksum here to be 0, but that's easy. So, the famous redirect to localhost bug. This is one of the things that drove me to dive into this. A packet that comes from the local host. The scenario that showed this is when you redirect something to localhost, the reply packet from local proxy, like relady. You redirect to localhost into relady does something and replies. This packet coming from the localhost has the pseudo-header checksum from the template TCP. From the upper layers of the stack. The template TCP isn't that, right? Then PF rewrites, because the packet had been redirected to localhost, so we have to, in the reply packet, we have to exchange the source address to the original destination, right? So we rewrite that packet. Of course, for this rewriting, we have to update the checksum. But PF cannot know whether the packet has a full checksum or a pseudo-header checksum. So if we are changing something in the TCP header, we'll happily update the checksum. But the checksum in there does not cover that part of the header yet. Result is obvious, the checksum's broken. Yes. So there's 3 cases to consider. The software engine doesn't care. It just does a full recalculation of the checksum now. It doesn't do this updating crap anymore. The same hardware doesn't care because it just recalculates the checksum and writes it to the packet. But Intel and Broadcom, relying on the pseudo-header checksum to be there, you're obviously doomed because now they're updating a broken checksum for the payload, and well, surprised, it's still broken. So those packets will be thrown away by the destination host because the checksums don't match. The result of that is that we had to disable protocol checksum offloading completely on these cards because, well, that's just broken. And that, last not least, is EM, BGE, and BMX as in 90% of the server market. As with the IP checksum, pretty much everything that's made in this decade supports it. Not necessarily 556, but that's irrelevant anyway. Unfortunately, there are many silicon bugs, like bugs in the hardware. We've seen the case where when you turned UDP and TCP checksum offloading on, the hardware would corrupt OSPF packets.
Yes, specific prefixes would cause corruption.
Yes, of course, the TCP UDP checksumming engine has no point even touching an OSPF packet. That's a different protocol. Hardware. Just as with the IP checksum, the bridge was special and needed care. Basically the same problem, and basically this has been fixed in one go with the fixes I did for the IP checksum. However, dealing with the protocol checksum is considerably more complicated because there's 3 cases we have to consider. With IP it's easy, offloading or no offloading. Here it's 3, it's no offloading, the pseudo-header checksum required offloading, or full offloading where it doesn't care about the pseudo-header checksum. So what did I change? We always want to work under the assumption that we have an offloading engine, because almost everything these days has. If we're hitting a path that does not have any offloading capabilities, because it's a stupid network interface card, or it's an IP set card, or anything like that, we'll just call it the software engine, basically emulate the hardware offloading engine. All this magic is in the new functions, IN and IN6, proto checksum out. basically what they do is they check the flags. If there's checksumming needed, they either call the software engine or pass it on to the hardware with the right flags set to request the checksum from the hardware. For IPv4, there was IN delayed checksum. That's basically the software engine, and this didn't have to be modified really. For V6, there was no such a thing, so we had to write that, which was once again a pain in the because just finding the TCP header in an IPv6 packet is a nightmare. In V4 it's easy, it's a fixed offset. In V6 you have to walk the entire chain of extension headers. And, anyway. So, to make better use of the offloading engines, we are calling the proto checksum out functions very late now. And we are not pre-calculating the checksum anymore. We're taking the decision whether we have to do checksumming or not very late. But we certainly know on which interface the packet's going to go out. Which means that we can remove almost all other checksum handling from the stack. I call this de-Bill-joying the stack. Bill Joy, it's all his fault. All the spaghetti code in the network stack is Bill Joy. Whereas he was adding one hack after the other. He was certainly brilliant, but the code that he wrote, sorry, is shit. It's spaghetti code. He all over the stack. Instead of calling APIs, he's like, oh, wait a second. I know the inside of this. I have inside knowledge. So I fiddle. What do I need APIs for? So if you want to make changes to the stack, you're fucked. So that's what we're still dealing with now, 20 years later. That, as said, is part of the journey. You can remove the checksum handling from basically all the stack and all OPF. Just set a flag if we need checksumming, and the checksum code is nicely self-contained in one spot and does the right thing, does the magic. If you want to change anything there, it's one spot and not spaghetti all over the stack. ICMP has a checksum too. There is, as far as I know, there is a single bit of hardware, a single piece of hardware that has an ICMP checksum offloading engine. That doesn't quite seem to make sense anyway, because ICMP tends to be not performance critical. But we don't want spaghetti handling for ICMP and nice code for TCP and Unity, right? So I remodeled the ICMP checksum handling, but the very same way that we did for TCP and UDP. We'll just always end up calling software engine. So what? Not a problem. ICMP errors are interesting. Of course, ICMP error messages, error packets quote the TCP or Unity, usually TCP or Unity packet, might be something else, but we consider the TCP and Unity case here. They quote the packet they refer to. So if you're sending a TCP packet, say you're trying to access some web server, and an intermediate router has no route to that destination, it sends the ICMP unreachable back, right? And this ICMP unreachable has parts of your original request in it. It gets quoted so that you can match this ICMP error to the TCP session that it belongs to. Now, when we do NAT, it's kind of obvious that we don't just have to rewrite the addresses on the outside. We also have to rewrite the addresses in the quoted packet, because otherwise the sending host cannot match this ICMP error to the TCP connection. But when we rewrite the addresses, well, that quoted packet, of course, has a checksum. In most cases, it'll be truncated, so we don't care. On a truncated packet, there's no way to verify the checksum, so we don't need to do anything. But there are very, very small packets that don't get truncated, and this checksum is verifiable. Fortunately, there's nothing, at least I didn't find anything, and we looked up and down, there's nothing that cares about the checksum in the quoted packets, except for one thing, Scapy. That's a network testing thing that we use quite extensively because you can generate really, really weird packets with it and throw them at the app and see what's doing. That's the only thing we know that actually verifies the inside checksum. But well, I have not implemented this, but handling that case is easy enough if you figure out that the packet is not faulted, which is easy to figure out because you have to look at the MP header in the faulted packet anyway. So there's the length, and if that length matches the data length, you're fine, and it's not truncated, then you could just recalculate the checksum by just calling the regular functions. As said, I haven't done this because nothing cares anyway, but we could. We probably do at some point. So, consequences in PF. The old way of handling the checksums was to update it incrementally, right? The new way is, I don't care, I did a change to a packet, set a flag, it has to be recalculated. If you update the broken checksum, like the packet already comes in with a broken checksum, and we update it for the changes we do, the checksum is still broken. So that's good. But if you do all these changes and just set the flag, oh, this packet needs checksumming, and the engines at the end rechecksum the packet, the checksum is valid. We just fixed it. Oops. That's not supposed to happen. So before rewriting the checksum, you actually have to verify it. And unfortunately, this is potentially expensive because it covers the entire payload. So, yeah, this is like no way about this spreadsheet. Still, now the question is it worth it, right? Why don't we keep the updating way? Why? The code is so much easier and cleaner. It's not the spaghetti bullshit anymore. It's nice and self-contained. So we want that. There's even much, much, much more cleaner possible afterwards. And eventually we'll have a really nice memory snake. This fixes the redirect to localhost bug, obviously. It allows us to enable the protocol checksum offloading on the cards that require the pseudo-header checksum. And as said, this is foremost EM, BGE, and BMX, which is 90% of the server market. So that's where it matters. There's unfortunately one case that suffers considerably from this change. And that's my presentation food crashing. Wow, I've never seen that before. It's Japanese software, by the way. Magic Point was almost completely written in Japan by Japanese people. And it's awesome. Except that it isn't. It isn't most of that, or much of that. Now my timer is up. Anyway, yeah. Yes, the case that suffers considerably is when we are doing rewriting. When I say NAT here, I mean any form of NAT, be it rewriting the source or destination ports or addresses, all these, like the generic term. When we do NAT and do not have any offloading capabilities, as mentioned, this is very unlikely on recent hardware, that of course suffers because it has to verify in software and recalculate in software, which means it has to fetch all the payload from memory. I think that case doesn't really matter. Because one, you have offloading capabilities everywhere. Two, we're really micro benchmarking here. If you're doing anything more than just forwarding, the cost of that anything more hides the cost of the checksumming and the forwarding anyway. What we could do to fix that case, we could checksum just the headers without touching the payload before PF does changes. Then do our changes, then checksum again to basically apply the delta. It's not straightforward to write, but it's possible. This would let us not use the offload engines in that case at all, unfortunately. And the software checksum headers and apply delta thing is not free, of course. So we are hurting the offloading case to support something on ancient hardware that you should just throw away. Have again by Le Computer. The offloading is not just there for everything, it becomes even more common, right? So that's the case I rather optimize for than for old stuff. if you care about performance and run a Spark from 1995, you're doing something wrong. So in micro benchmarking, we lose 5 to 10% depending on the traffic pattern. Actually, there's one case that looks really, really, really evil. There's 25%, but this is not even micro benchmarking. It's even smaller. Like that's a constructed case, basically. And this is all on AMD 64. That also applies to x86, of course. How much you lose depends a lot on the specifics of the hardware. As I keep mentioning, cache is critical here. So cache size makes a whole lot of a difference. The cache architecture makes a whole lot of a difference. How many layers of caches, that makes a whole lot of a difference. So by just measuring this on one machine, you are not getting the complete picture. But obviously, I don't want to run these tests on 100 machines. Why do I keep mentioning this? We did all benchmarking on AMD64. But this is an architecture that almost guaranteed has these offloading capabilities. So even if we manage to construct a case there that's hurt badly, it doesn't matter in practice. So I find using 5 to 10% in that case, with the advantages that all the other cases that actually matter get, very acceptable. And well, have again, buy a computer or a network interface card. Buy some USB dongle. They don't have even those do checksum offloading. So spend 100 yens on a USB dongle. So performance changes from the checksum offloading. On a really recent AMD64 system, like a current Xeon CPU, and doing pure forwarding, we still cannot measure any difference, unfortunately, because it's what I explained earlier. The raw processing power in these is like they're so fast that the offloading doesn't help them at all, because the limiting factors are not the CPU, it's latencies to the devices and everything. Running the very same tests on an older machine with Pentium M, I get about 7% increase. That's considerable for something optimized that much. Yep. Future work. The code that, after the de-spaghettied code, that paves the road for future improvements, because now it's actually readable, understandable, and followable. Last but not least, it's less code, and it's nicely contained in one spot. I keep mentioning this, of course, the build-joy effect, right? It's in one spot, so if there are substantial changes to that ever again, it's one spot, actually two before V6, but easy enough to modify and not a gazillion files all over the network stack. Because that is completely in and proven to be somewhat stable, we can remove the stupid pseudo-header checksumming from the TCP and UDP stacks completely, because there's no point in doing the pseudo-header checksums. You'll just do the complete checksum in the output part. That's cheaper. And of course, the special casing of the bridge has to die. This will happen eventually. If somebody wants to beat me on it, be my guest. I have to acknowledge a couple of things here, because that was a major task. We briefly touched the surface. The checksum handling in the stack is much more complicated than I ever imagined. If you're reading up on checksumming, it should be super simple. And then you start reading the code, and you keep being surprised. I've been working on the network stack for 10 years, but it was not clear to me what a mess the checksum handling was. Christian Weisgerber, that's an A, was the first one who actually understood what was going on with the redirected localhost problems. It's very hard to figure out why this suddenly doesn't work anymore. He explained that to us, the PF hackers, more than once. It took several attempts until we got what he was talking about. And now, when I finally worked on this, like we've been talking about this for about 4 or 5 years, when I started working on this, he did a lot of testing and verifying my code. Like, he helped a lot. Thanks for that. A lot of testing, help, and support came from Mike and Peter. Thank you. Especially benchmarking, because they have access to nice benchmarking hardware, to the XCR systems. And the IPv6 version of the delayed checksum handling was written by Ken. Thank you, Ken. I didn't have to touch that list. I actually started working on that in 2010. That's 3 years ago. There were many, many hackathons and conferences that I used to proceed on that. There's the list from Iceland to Slovenia, Canada, Germany to New Zealand, with the people, the main persons organizing this. And there's been the conferences. EuroBSDCon, AsiaBSDCon, and BSDCon. You should go to all 3 of these conferences. They're really awesome. That's my talk. Any questions?
Why the gloves?
Did you just ask that?
I did.
Oh, that's cheating.
On behalf of the silent
To
masses.
show respect to the workers. Oh no. The gloves. We figured this out last year. Everybody in Japan doing something semi-official is wearing white gloves. Whether you're driving a taxi or driving the subway or being a policeman, you are wearing white gloves. So I'm standing here giving a presentation. I should wear white gloves. I'm showing respect to your culture. Which I really like, by the way.
Hi. May I have a question? Thank you very much for your interesting
I can't hear you.
sorry?
I can't hear you.
Sorry. I must be loudly. Okay. Do you have any idea how many NIC support hardware IP checksum functions now?
You mean how complicated this is to do
So,
hardware, or?
I'm sorry?
How many NICs?
How many NICs? So
like
there
in-
are so many NICs supporting
like in percentage?
IP checksums. So
Like
if it's
the
necessary
percentage of
for
all of them on the market now?
now, or I mean,
It's-
how software IP checksum is necessary in actual cases? I want to know.
Yeah, you want to know how often is it really necessary on modern hardware to do the software checksum?
Almost never.
Almost never.
Almost never, because you almost always have the hardware offloading. The most common case where you need to do the software checksumming is IPsec. Sorry, if you're doing IPsec, the cost of checksumming the payload doesn't matter.
Yeah.
You touch all the payload anyway because you're encrypted, so the caches are not an issue anyway. So that's the most typical case now. Otherwise, almost everything has offloading. There's the other case that's kind of common where you have to do software is tunneling. But then the tunneling is more expensive than the checksumming tool.
Yeah.
So it's not a performance critical or performance relevant case. The only performance relevant case is the one I mentioned. You do net and nothing else and do not have any offloading. And that basically does not exist anymore. It exists with some very, very new hardware where the driver does not yet have the offloading support code. But, well, that's an omission usually. And so far, since the offloading didn't really play out, the motivation for people to add the offloading support to the drivers wasn't all that high, right? Now, if it does play out, the motivation is different, and there you do it.
Thank you.
Thank you.